All right. So thank you to Brad and Nat and the rest of the speakers this morning for a really great introduction to some of the material I'll be presenting today. So today I'll be discussing some of the compositional markers of deep SPA ejecta and how we can use remote sensing data to identify promising areas in the Artemis exploration zone to collect this material. So it's important to note that some of these same compositional markers can be detected by in situ observations. So what that means is that it can help us optimize sample selection once we're already on the lunar surface. One of the biggest takeaways here is going to be that context really matters. So SPA is so large and so complex that it contains nearly the full range of lunar surface compositions in one form or another. So there's no specific compositional markers we can point at to uniquely identify SPA materials in the Artemis exploration zone, but we can lean on some of this geologic context and these integrated compositional analyses to maximize our likelihood of sampling SPA material. Next slide, please. So I'm not going to be spending much time on the kind of motivation and implications for sampling SPA because that's been really well covered by some of the previous speakers today. So instead, I'll be focusing on some of the materials unique to SPA that are most critical for addressing decadal level science questions. And so in the Artemis exploration region down at the lunar South Pole, there's emerging compositional evidence that SPA ejecta should be present. And there's also a good chance that this ejecta will contain materials that were melted during SPA formation, which records the age of the basin. Yep. So as we know, understanding the evolution, the formation and evolution of the moon's initial differentiation, and then its crust and mantle is a really high priority science goal with wide-ranging implications. We currently don't have any confirmed mantle materials in the lunar sample collection. So our understanding of lunar differentiation and the structure of the mantle is derived primarily from geophysical observations, models, and experiments on lunar samples, things like Mare basalts and volcanic glasses. So identifying and characterizing some of the deep materials that have been exposed at the lunar surface is really critically important for advancing our understanding of the moon. Next slide. So SPA should have excavated mantle materials or other deep materials. So what do they look like and where are they located? Next slide, please. So the initial structure and subsequent evolution of the lunar interior is not fully known, and this is one of the high priority science questions we're trying to address through SPA samples. But we do have a pretty well-developed sense of the basic processes and building blocks. So we know that the early moon was molten to depths of several hundred kilometers or more. As this magma ocean cooled, mafic minerals olivine and pyroxene crystallized early and sank, while late crystallizing lower density plagioclase rose to form a flotation crust. So this remaining liquid in the magma ocean becomes progressively enriched in iron, titanium, thorium, and some of the other incompatible elements that we know collectively as creep. So these elements are really concentrated in the last cumulates to crystallize, and these include things like iron-rich clinopyroxenes and titanium oxides. Some of these late-stage cumulates end up sandwiched between the sinking mafic cumulates and the buoyant plagioclase. So we think that SPA should have excavated entirely through this flotation crust. And what we want to know is there evidence for excavation of these late stage cumulates or maybe even the underlying mafic mantle? Next slide, please. So here we're looking at a recent three-dimensional impact model, which in this very specific set of parameters demonstrates the most likely distribution of deep materials ejected by the SPA forming impact. Here we're showing this predicted distribution of deep ejecta in this black to red gradient. But one thing to keep in mind is that SPA is really ancient, and its ejecta blanket has been reshaped and diluted by billions of years of complex geologic processes. So we've got mixing, subsequent impact, volcanic resurfacing. So here we're showing this partially by superimposing a map of subsequent impact craters on the predicted SPA ejecta distribution to get a sense of where this ejecta blanket might be really well preserved, and in other places where it might be locally removed by large impact structures. Next slide, please. So if this deep SPA ejecta has been preserved at the lunar surface, it might follow a similar kind of crescent-shaped distribution. Next slide. And so in fact, that might be exactly what we see. So on the left, we're showing a map of thorium abundance from Lunar Prospector. And as you'll recall, thorium is one of those elements that gets concentrated in this late stage magma ocean cumulate pile. So this is suggesting that SPA may have excavated through the flotation crust to expose these late stage lunar magma ocean cumulates, which maybe we can refer to those as the uppermost mantle. Next slide, please. Some of the geologic correlations here seem consistent with this origin. So we're seeing that local minima in thorium abundance are correlated with areas of volcanic resurfacing and also some large impact structures like the Apollo Basin, which could have excavated entirely through the SPA ejecta blanket. Whereas some of the local maxima in thorium are correlated with smaller impact structures, these kind of complex crater size, 50 to 150 kilometer impacts, which might be kind of re-excavating SPA ejecta from beneath a kind of mixed and diluted regolith layer. Next slide, please. So this interpretation is further supported when we compare some of the associations between thorium abundance with some of the other compositional maps that we have for SPA. So on these maps, we're showing the thorium abundance by contour lines, and you can see the highest thorium abundances are concentrated in northwest SPA. But what we see is that this area of highest thorium abundance is also correlated with elevated titanium, iron, potassium, and clinopyroxene abundance. So these are all present in Northwest SPA, and these are spatially correlated with the areas of highest thorium abundance. These compositional properties are all consistent with an origin as these late stage lunar magma ocean cumulates. This is kind of exactly the assemblage you would predict to see. But what's interesting is that the absolute abundance of this material might be low. So if we look at the M-cubed 1 micron band depth map here, we're seeing that it doesn't necessarily have a high abundance of mafic minerals. It's certainly lower than the abundance of mafic minerals you have closer to the SPA interior, where you have the impact melt sheet. But if you think about it, that actually makes sense. Next slide, please. So if you assume a kind of roughly hemispherical geometry for the SPA ejecta volume, what that tells you is that the shallowest materials volumetrically dominate the ejecta blanket. And one thing to keep in mind is that that would be especially true in the uprange direction, where the depth of excavation is a little bit shallower. So in other words, SPA ejecta inherently include a significant fraction of crustal material. And at the South Pole in particular, this crustal material might dominate the SPA ejecta, which could make those ejecta hard to distinguish from some of the pre-existing substrate that those ejecta were placed onto. Either way, the deepest SPA ejecta in this mixed ejecta blanket are then further diluted and obscured by 4 billion years of geologic evolution. Next slide, please. So we've seen that iron, thorium, and mafic minerals seem to be well correlated with this predicted distribution of deep SPA ejecta. So what do some of these signatures look like across the Artemis exploration region? So here we're showing maps of lunar prospector thorium on the right and Kaguya-derived iron abundance on the left. And we've highlighted the kind of list of 13 original candidate Artemis 3 regions here. So in this view, SPA is towards the bottom left of the map. And so as you can see, both iron and thorium here show a pronounced gradient with distance from SPA. Now the absolute abundances here are fairly low, but what's encouraging is that there's good spatial correlation between these two different instrument types that are measuring very different things on different spacecraft that flew decades apart. One limitation of the data we're showing here is spatial resolution. So the Kagoya iron maps are available at 1 kilometer per pixel, and the lunar prospector data is available at tens of kilometers per pixel down at these latitudes. So these are not particularly useful products for traverse level decision making. So one thing we want to do is investigate higher resolution data at one specific site to see what information we can get from from full resolution data. So of these 13 candidate Artemis 3 regions, it's the Dagurlash Kosher Massif down here, which has the highest iron and thorium content. And it's also, not coincidentally, the closest site to South Pole Aitken Basin. Next slide, please. So at the Dagurlash Kosher Massif, we've conducted an investigation using the full resolution moon mineralogy mapper data, which is available at about 150 meters per pixel. And the idea here is to look at the local distribution of mafic minerals and identify possible science targets for sample return or in situ investigations. So here we're showing Lola topography on the left and a mafic mineral map derived from a PCA deconvolution of M-cube data on the right. So with this approach, we were able to identify several small fresh craters with a distinctive mafic signature. These craters have sharp rims and ejected boulders, and those can be seen fairly easily in NAC imagery. So to be clear, I'm not showing these maps to advocate for a specific region or site. Instead, this is kind of more of a demonstration of the types of analyses we can do with some of this remote compositional data to identify and characterize possible science targets within specified regions of interest. Next slide, please. So with M-cube data, we can also determine the composition of pyroxene-bearing lithologies using the positions of the 1 and 2 micron spectral absorption band centers. So we're showing that here on the left. We're plotting the 2 micron versus 1 micron absorption band centers. And there's a systematic relationship between these band centers where we have iron and calcium-rich clinopyroxenes plotting with long wavelength absorption bands, whereas the more magnesium-rich orthopyroxenes plot with shorter wavelength absorptions. So when we plot these small mafic craters on the Dagurlash Kosher Massif, comparing it to some of the other materials we see around SPA, we see that these, which are plotting here with these triangles, so these are plotting fairly far from the iron, from the composition of the thorium-rich materials we're seeing in Northwest SPA. So these are perhaps a different composition than these thorium-bearing late-stage lunar magma ocean cumulates we see somewhere else in SPA. They're plotting more on this population of the neritic materials we see in the SPA interior. So could these be SPA ejecta from shallower or deeper depths than the thorium-bearing material? Maybe. So in the next talk, Jeff Andrews Hanna will dive a little bit deeper into some of the geophysical understandings of the SPA basin and its formation. And so we'll get more into some of the details about what these neritic materials around the South Pole could be if they are indeed related to SPA. Next slide, please. So to wrap up, so compositional remote sensing observations, including moon mineralogy mapper data, they provide key context for establishing sample return goals and then interpretation of those samples for Artemis 4. One specific material we looked at in terms of what deep SPA ejecta might look like is these late-stage lunar magma ocean cumulates. And we do see in remote sensing data that there's a good correlation between iron, thorium, titanium, creep, and iron and calcium-rich clinopyroxenes. And those also align well with one prediction for the region of deepest SPA ejecta. So we think these could be a really important tracer of this deep SPA ejecta, these late-stage lunar magma ocean cumulates. We do see that the Artemis exploration region exhibits a gradient in iron, thorium, and mafic abundance, and it decreases with distance from SPA. And then we can use full resolution data like M cubed to identify kind of these small scale mafic anomalies, such as small craters that would be relevant at the traverse scale. These small craters we've identified so far near the de Gerlache-Kocher Massif, they exhibit a low calcium pyroxene-rich composition, so they are not similar to the thorium-bearing materials we see in Northwest SPA. And that's it. Thank you very much.